Okay, so let's continue. Yesterday's lecture, we said that uh, there are several regions in which MOSFET can operate, and this is a picture of how we can divide the operating range of a MOSFET. First, on the basis of threshold voltage, we can classify MOSFET operation above threshold voltage or below threshold voltage. Below threshold voltage, we call it subthreshold. And then if it is above threshold voltage, we classify MOS operation either in saturation or in triode, and that's on the basis of this voltage called VD-SAT here. So two voltages, threshold voltage and saturation voltage, which help us to classify different modes of operation of the MOSFET here. So as I said, the most important region for us is the saturation region. That's where we will bias our MOSFETs in order to make amplifiers. And but let's look at how MOSFET operates, or what is its behavior, one by one. First in triode, then in saturation, and then in subthreshold. Okay. So first one is the triode region is the one that you see over here, triode, and also called linear because the current here at very low voltages varies linearly with voltage here. And so this is the region of operation. So note the transistor is biased above threshold voltage. That's the first thing. And the second thing is the transistor drain to source voltage is less than VD-SAT, the saturation voltage, and saturation voltage is VGS minus the threshold voltage here. Okay. So we are talking about this part of the operation here. And in this region, the current changes with voltage in this particular manner here. It changes linearly with gate to source voltage here. IDS is VGS minus VTHN. Somewhere you will see, I've not been consistent in the use of symbols. Somewhere you'll see VTHN, somewhere you'll see VTN. These are all the same thing, threshold voltage, okay? So VGS minus VTHN, that's the first term, multiplied by VDS, minus VDS squared by 2. And there is a parameter called beta N here. And beta N can be further broken down into two parameters. KPN, called the transconductance parameter. W is the width of the MOSFET. L is the channel length of the MOSFET here. Okay. KPN, if you wish, can be further broken down into mobility multiplied by the capacitance per unit area. Now, typically what will happen is once you're given a MOS model or once you choose a particular MOS technology, KPN is fixed for you and L is also known. Often what happens is different MOS technologies are classified as, you will hear the word 0.5 micron MOS technology or 0.18 micron MOS technology. Now what it refers to, if you're hearing the word 0.25 or 0.18 micron MOS technology, what it means is that the minimum channel length that you can get is 0.18 micron. If somebody says, I'm working with 90 nanometer MOS technology, it means the minimum channel length that you can make L is 90 nanometers. Of course, you can make L larger than that. If you want, you can make 180 nanometer and 250 nanometer and all that, okay? But the minimum L is the 90 nanometer. Now, depending on the technology that you choose, okay, 90 nanometer or 0.25 micron technology or whatever, what happens is the moment you choose a technology, KPN gets fixed for you. You don't have control over KPN. KPN depends, technology means the way the MOSFET has been manufactured. So KPN becomes fixed for you, mobility, oxide capacitance, you don't have any control over it. So KPN is fixed for you. Minimum L is also fixed for you. And typically what happens is many times, when we design MOS circuits, we often take L as the minimum possible. Minimum possible because you will see later on the speed of the MOSFET or the frequency response, all of that depends on L. The smaller the L, the faster the MOSFET. So whatever my technology allows, if my technology allows me to make a minimum MOSFET of 90 nanometer, most of the time I will use 90 nanometer. Okay, sometimes you deliberately use L larger also. There are benefits of that in other contexts, but many times we choose L as minimum possible. Okay, so what happens then is, if you look at this equation, KPN is fixed for you. Many times L will be decided by the technology also. So as a designer, the freedom that you have is, you can decide what value of W you choose. You can have W of any dimension as long as it is larger than the minimum dimension. So if I'm calling it 90 nanometer technology, W has to be larger than 90 nanometer. Okay, so with that constraint, you can choose W, any value larger than that. So W is under your control. As a circuit designer, W is under your control. You can decide what size of MOSFET to use. And of course, VGS is under your control. VDS is under your control. Threshold voltage is again fixed. Once you choose a technology, threshold voltage gets fixed here. So this is the equation that describes the operation in this particular part of the operating region here. You can see that if your VDS is small, applied drain to source voltage is small, then the second term, quadratic term, is negligible compared to the first, and you can see then IDS is beta VGS minus VTH and VDS. So it's linear here. Okay, so you start off linearly. Basically, the first term is dominant, and then as you increase VDS, the second term becomes more and more important here, and the curve starts bending. Starts bending because of this particular part. So anytime the MOSFET is in triode or linear region, this is the equation that you need to use in order to model current versus voltage behavior. So current again depends on drain to source voltage here and depends on gate to source voltage here. Okay, so that's the parameter. So KPN will be provided to you, KPN will be provided to you. VTHN will also be provided to you, so you can calculate whatever is the current. So that's the triode region here. And note the condition that you have to use in order that you have to satisfy in order to use this equation is this one here. Transistor has to be above threshold and drain to source voltage has to be smaller than VD sat. That's the condition. Okay. Our today's quiz will be based on these two constraints. Okay. So I think everybody is alert now. This condition here. All right. Saturation region. Saturation region we said is here. So saturation region is here, and the condition for this is again the transistor has to be above threshold. The transistor has to be above threshold, and the transistor has to be biased at a drain to source voltage which is larger than VD sat here, VGS minus VTH. So you are in this region here, and as you can see the current is almost constant, and this is the equation that you use here. IDS is beta n by 2, VGS minus VTHN square, 1 plus lambda times VDS here. Okay, lambda is what is called as the channel and modulation parameter, and note again lambda n will be given to you, so you know lambda n, VTHN also you know, and beta I've already explained. So you have all the parameters that you need, and if once you know the gate to source voltage, you can calculate whatever is the current. As I said, this parameter is small. Lambda may be, as an example, lambda may be 0.01. Lambda may be 0.01, and note that if you have 0.01 multiplied by 1 volt or 2 volt, you're talking about a value which is 0.02 or 0.03, something of that sort. Okay, so it doesn't make too much difference to the current that you see here. The more important effect of lambda would be in the output resistance. When we calculate output resistance, that directly depends on the lambda here. So in the DC current equation, lambda doesn't have that large an impact. Okay. So this is the then simple equation. It predicts that current increases quadratically with gate to source voltage. And there's a small, you can hardly see it. There's a small change with respect to VDS here, which is represented by this equation. Okay. All right. So note, if you look at now, one point that you have to note, the saturation region begins at VD sat. And VD sat, as you can see here, is VGS minus VTHN. So the beginning of saturation region depends on where you bias your transistor. Depends on gate to source voltage. So if you look at this particular figure, this shows you drain current versus drain to source voltage here. You can see saturation begins here. At this point, at this point, at this point. This beginning of saturation region is changing. Because in this case, the gate to source voltage is 2. So saturation region begins at around 1. In this case, it is gate to source voltage is 2.5. So saturation region begins at 2.5 minus 1, which is 1.5 here. And in this case, again, it begins at 2 volt here. So the beginning of saturation region depends on what gate voltage you bias at. 3 volts, 2.5, 2 volts, and so on and so forth. All right, so this is the parameters then. Note, linear region. This is the equation that we have. Saturation region. This is the equation that we have. And these are the parameters that you need in order to use the model. You need to know what is KPN. You need to know what is L. You need to know lambda n, VTHN0, and 2 phi f and gamma. Once these parameters are given to you, VTHN0, gamma, 2 phi f, lambda n, KPN, L, then you are in a position to calculate the current depending on whether the MOSFET is in linear or whether the MOSFET is in saturation region. And throughout this course, these are the typical values that we'll use. VTHN0 will be 1 volt. Gamma, which is called the body parameter, describes the dependence of threshold voltage on source to body voltage, will be 0.7. 2 phi f, there's a name for it called surface potential, but it's a constant, 0.7. KPN, 100 microamperes per volt square. Throughout the discussion, we'll take lambda L equal to 1 micron MOSFET, and lambda for us will be 0.01. Okay, so these are the typical values that we'll take in order to work with the MOSFET and design amplifiers. We have several questions. The first one is, a transistor is given to you with the following voltages: 0.7 to the drain, 0.5 to the source, 2 volt to the gate, and body to source voltage is not shown. The body is connected to source, so VBS equal to 0. The threshold voltage is 1, and we are asking which mode is the transistor operating in, meaning is it in linear region, is it in saturation region, or is it in subthreshold region? These are the 3 ones: linear, saturation, subthreshold. So find out which mode is the transistor working in, and give reasons for it. VGS is 1.5, 2 minus 0.5, so we have 1.5. VDS is 0.7 minus 0.5, 0.2, and VDSAT is VGS minus VTHN, so it's 0.5. That's VDSAT, and so we find that VDS is less than VDSAT, so it's linear. All right? Okay? That's the next problem. It's the same procedure here that has to be repeated in this case. Okay? So let's look at the solution. VDSAT, 0.5. The moment you're given VGS, which is 1.5, so VDSAT is 0.5 here. VDS is 1, so it's saturation. Okay? So the question is it in linear, is it in saturation, or is it in subthreshold? It's a trick question. Think again. Think again. Is it still in subthreshold? Yes? Yes. Still in subthreshold, okay. All right. VGS is minus 0.5. I guess all of you are thinking 2 minus 0.5. Right. VGS is 0.5. VDS is minus 1. But now look at the transistor. Saturation? Okay. Look at the transistor. I'm calling this as source and this as drain, right? I mean, does your transistor know which is source and which is drain? I mean, it's up to you what you're calling, right? I can as well call this as the drain and this as the transistor doesn't know that. Both terminals are exactly the same. The transistor is symmetrical, right? The transistor is symmetrical. I am calling it, gate is of course unique. Gate is connected to the insulator here. So gate is unique. The source and drain that you see here can be interchanged. I can call this as source and this is drain, or I can call this as drain and this is source. So when I apply 0.5 volt here and 1.5 here, the diagram of course is saying this, the arrow and all that is showing this is source. But you could think of this as a drain and this is a source. right? So if you think like that, then of course, you can work it out. You will find that this becomes source, this becomes gate, then you have VGS, which is 2 minus 0.5, 1.5, and it's larger than 1, and therefore your transistor is actually on. Transistor is actually on, and then and VGS is 1.5, and VDS is 1 here, and so you can calculate then that the transistor is actually in saturation. So the idea behind this particular problem was to make you realize that MOS transistor, unlike bipolar you cannot interchange emitter and collector. They're very different. Okay, here the source and the drain are exactly the same. You can interchange source and drain, and the transistor works just fine. Exactly the same way. Okay, so just because I've put here 0.5 and 1.5 doesn't mean that this has to be source. The transistor will take this as a source and this is a drain, and the current will flow from this terminal to this terminal here. Okay, what about this one? Okay, so this is in saturation. VGS is equal to 2. VDS is also 2. And therefore, remember the condition for saturation is that drain to source voltage should be larger than VD sat. VD sat in this case will be 2 minus 1, which is 1 volt here. So VDS is 2, VD sat is 1, and VDS is larger than VD sat here. This particular is a very simple circuit, has a interesting characteristics. As you can see here, the transistor is in saturation, and if I neglect this second part here, second part 1 plus lambda VDS is a small part here. So note that the current between these two, so it's a 2-terminal device now. The moment you take gate and drain short together, I have 2 terminals, and current is beta by 2, whatever is the voltage I apply here, let's say Vx minus VTHN square, right? And note that this is when Vx is greater than VTHN. And if Vx is less than VTHN, the threshold voltage, this whole device is like a cutoff state and doesn't carry any current. Okay, or carries negligible current. Yeah. Especially if you make Vx much smaller than threshold voltage. If you make Vx as threshold voltage is 1, if you make Vx as 0.5 or 0.1 or 0 or negative, you find that there is hardly any current flowing. So what does this remind us of? If Vx is greater than VTHN, you have significant current which starts flowing. If Vx is much less than VTHN, you have no current. Okay? It's like a diode. This one is like a diode, except that instead of 0.7 volt cutoff, what do you have? VTHN as a cutoff. Okay, so VTHN equal to 1 volt. So very often in circuits, in MOS technology, if you want a element which behaves like a diode, what you do is you take a transistor, short is gate and drain together, and these 2 terminals then can act like a diode. It can rectify, it can do all of those things that you can do with a diode here. Except, of course, note that the onset, the turn-on voltage is large here, 1 volt, as compared to a regular diode. And the other problem with this one is a regular diode is very sharp, it's exponential, and this is only a square law. Okay, so while a regular diode you can easily approximate by saying that once the diode is on, you say the voltage is about 0.7. In this case, the characteristics is not very sharp. So even though it is on, you cannot say the voltage across your diode remains at around 1 volt. The voltage keeps on changing. Okay, so those are the differences that you must keep in mind, that yes, you can use it as a diode, it acts as a rectifier, but the characteristics is not as sharp, is not exponential, and therefore the voltage drop across your MOS diode will keep on changing. Okay, so it's in that sense, it's not a very good diode. All right, so this is this obviously now I have regular drain source and 1 volt here, so VGS is less than VTHN, and the transistor is in sub-threshold mode of operation here. I've talked about current. I've talked about current equation, and this is the current equation in saturation. Now, this is the current equation in saturation, and if you look at this equation, the current increases, or the current changes with temperature, and the reason for this is 2. in all these parameters that I note here, of course, gate to source voltage is under my control, so I can keep it fixed. What happens is W and L are physical quantities. They don't change with temperature. So with temperature, what happens is threshold voltage changes, and this value Kpn also changes. And both, what happens is threshold voltage actually decreases with temperature. If you make temperature higher, threshold voltage goes down. And if you make temperature higher, then Kpn also goes down. This one also goes down because this parameter depends on mobility, and mobility of carriers becomes less as the temperature increases. And so this parameter decreases here, and this parameter also decreases here. And this kind of complicates life here, because a decrease in this parameter implies that the current increases, while a decrease in this parameter implies that the current actually decreases here. So what happens really depends on which term is stronger. Is this stronger as compared to this one, or is this stronger as compared to that? And let me show you two examples here. Look at these two cases, these two circuits here. I have applied 1.2 volts to the gate in both cases, 1.2 volts to the gate. The transistors are biased in saturation region. Drain voltage is larger than the saturation voltage here. This transistor is at 25 degree, and this one is at 50 degrees here. And note, the current here is 20 microamperes, the current here is 23.65. The current here is larger than the current here. Okay, and so which term is obviously dominant? The threshold voltage. The fact that the threshold voltage is smaller here implies that the current is larger in this particular case here. Okay, now look at this case here. Gate to source voltage is raised to 3 volt and 3 volt here. Now note, the currents are almost same, with current at 25 degrees a little larger than the current at 50 degrees here. Okay, so why has this shift occurred? Can everybody see why now the behavior is different as compared to this one? Note that if VGS is small, as you can see from this equation, if VGS is small, then the impact of VTHN is larger, right? Any change in VTHN is significant then because VGS is small. While when I make VGS large, 3 volt here, a change in VTHN doesn't have as much impact. And therefore, KPN becomes more dominant. All right. So it's for that reason that you find that if you make your gate to source voltage small, your transistor the current actually increases with threshold, with temperature. On the other hand, if the gate to source voltage is large, either, it depends on the parameters. So I'm not saying that always the current at high gate to source voltage will decrease, but what it is illustrating is the dependence will be different, because it all depends on how threshold voltage changes with temperature, how KPN, and these things to some extent vary with the technology. Okay, so I don't want to make an absolute comment here that at 25 degrees, when you bias it at 3 or a large gate to source voltage, the current will always be larger than this. Okay, but you realize that the impact of VTHN becomes less at higher gate to source voltage as compared to the at a lesser voltage here. So that's something to keep in mind, because when you bias your MOSFET, remember, when you bias your MOSFET at some gate to source voltage, the current is going to change with temperature, and how much it changes it depends on the importance of these two factors. It is also telling you an interesting possibility that, if you look at this one, the current is larger. If you look at this one, the current is a little smaller here. So it also raises an interesting possibility that maybe there is a bias at which the current doesn't change with temperature, that the two terms here, they sort of cancel each other. Okay, so you will have in general different sensitivities depending on how you bias. How you bias will affect your temperature sensitivity. Okay, and as I said, in practical circuits, your circuits are supposed to work from maybe 0 degrees up to 80 degrees Celsius or 100 degrees Celsius. And therefore, these changes are important. One needs to take them into account. So among the MOS operating regions, we have seen the equations and the models for the following. We saw above threshold, and we saw that there are two regions of operation, saturation and triode. And today, as I said, most of the time, the transistor is going to be biased in saturation region. And this is one of the most important regions for us as far as amplifiers are concerned. And but nevertheless, let's take a look at subthreshold also, because many analog circuits, MOS analog circuits, exploit this particular region also. Okay, so let's look at this region quickly. And in order to understand this particular region, let's look at the transfer characteristics. Transfer characteristics meaning the drain current here along the y-axis plotted against the gate to source voltage here. We call it transfer because the current is being measured across, measured between drain and source, while the voltage is applied between gate and source here. So the voltage is between a different pair of terminals, and that's why we call it a transfer characteristics, in contrast to the case where we have drain current here and drain voltage also. We call that output characteristics. Okay, so we have a transfer characteristics here, and what you can see from this characteristics is that the current, our threshold voltage is around 1 volt. So what you see here is that the current, of course, keeps on decreasing with gate to source voltage here. And on a linear plot like this, what appears as that below threshold voltage, the current practically drops to 0. Okay, it appears as if the current is 0. The important word is appears. The actual current is not really 0 here, and this picture can be misleading. And many times students carry an impression that below threshold no current really flows, it's cut off. Okay, and that's not really true. What you can see here is that if you plot it on a log scale, you plot this current on a log scale, then you can see more accurately as to what really happens as you decrease the gate to source voltage here. Okay, so our threshold voltage, keep in mind throughout the discussion, our threshold voltage will be around 1 volt here. Okay, so this is all saturation region, and this is the region here. To the left of it is obviously below threshold voltage, and we call this as the subthreshold region. Okay, so this is what happens when you plot it on a log scale. If you see it on a log scale, and this is where my threshold voltage is. Okay, this is where my threshold voltage is. And so what you note is that, as usual, as you decrease the gate voltage, what happens is you have less and less number of electrons in the channel, and obviously the current goes, current becomes smaller. But note the difference here. Above threshold voltage, you can see here, there's a different kind of variation. Below threshold voltage, as you go, there's a different kind of variation. The two curves are qualitatively different. Above threshold voltage, we have already seen that if you're in saturation region, current increases as VGS minus VT square. It's a quadratic dependence above threshold voltage. It's a quadratic dependence. Below threshold voltage, if you ignore this transition region here, there's a transition region where you have neither quadratic nor this thing. If you ignore the transition region for a moment and you come here, what you notice, you see a straight line. And when you see a straight line on a log versus linear plot, it indicates exponential characteristics here. So what is happening is that as you go below threshold, here the current starts to drop exponentially. So current is not 0 below threshold voltage, you can obviously see. The current is dropping exponentially, and depending on how low you are compared to threshold voltage, the current is correspondingly as much smaller here. So current keeps on decreasing here. You can see maybe you start with 10 microamperes close to threshold. So even at threshold, for example, you have 10 microamperes current, and as you go lower, you find it drops to 1 microamperes, 100 nano, 10 nano, 1 nano, 100 pico, and keeps on dropping. Eventually, of course, you don't get this straight line. It doesn't keep on going. What happens is there are leakage currents inside your device. For example, the insulator that you use, the insulator is not really a perfect insulator. The gate, especially when the gate, the silicon dioxide becomes small, it allows leakage through the insulator. So you start getting leakage currents. Plus, if you recall, in a MOSFET, you have PN junction. Between source and body, you have a PN junction. And between drain and body, you have a PN junction. And PN junctions also have a leakage current here. So eventually what you find is that this current doesn't keep on decreasing, but will get limited by some leakage current. Okay, so these are simulation results, and in simulation, of course, it will keep on falling because we've not added the leakage component. So the important point to note is that current below threshold voltage begins to drop exponentially here, and this whole region is what we call as subthreshold. Now note that if you go considerably below threshold, then you are reaching this particular state here. You know, if you approach 0.2 or 0 or so, you're finding current is very small, and you can say, well, my transistor is in cutoff state. Cutoff meaning it's hardly carrying any current. But if you are here, obviously your transistor is carrying significant current. Smaller than in saturation region, but is carrying significant current here. So the issue is, how does my current vary here? Okay, so we can see it exponential, and so the model, I'm not going to give you the detailed model here. What happens in subthreshold is that the current goes exponentially with gate voltage, so e to the power q VGS by n kT, and depending on the how the MOSFET has been made, and there are many factors here, and n is usually larger than 1. Okay, larger than 1, and often in MOSFETs less than 2. Okay, so somewhere between 1 and 2 is where n lies here. And so current goes exponentially, and this should remind you of another device where current goes exponentially, which is the bipolar transistor, where the current goes exponentially with base emitter voltage. Base is an input terminal, emitter was a common terminal, so base emitter voltage. Here, drain current goes as exponentially with gate to source voltage here. And then transconductance, for example, ID, you can very easily calculate. GM is derivative of current with respect to gate to source voltage. So you get just similar to a bipolar transistor, IDS by NVT. In bipolar, it was simply IC by VT here. Here you get IDS by NVT here. So what is happening is that in subthreshold, MOS is acting like a BJT in terms of its this kind of a characteristics. The collector current, as I said, depends exponentially on base emitter voltage in a bipolar. In a MOS, the drain current depends exponentially on gate to source voltage here. Okay, so note that BJT is IC equal to IS e to the power VB by VT here, and MOS is also, IDS is some saturation current here, e to the power VGS by NVT. Okay, so MOS is like a BJT in subthreshold, but with the following differences that you have to keep in mind. The differences are that MOS is like a BJT, but unlike a BJT, MOS doesn't have a base current. See, the counterpart of base in MOS is gate, and gate, which means that the base gate current is negligible. Okay, so unlike a MOS, unlike a BJT, it potentially has a very, very high or almost like an infinite current gain. But unlike a BJT, the current in a MOS is very small in subthreshold, because remember, subthreshold is a region where I don't have enough carriers in my channel, right? So although it is exponential here, you see it exponential, but what happens is this current, in fact, I should have used a different symbol here for MOS, is giving an impression that IS here and IS here are the same. That's not true. So the currents in a MOS are much lower. Why? Because I'm in a subthreshold region here. You can see here as a typical example, you know, I'm at 1 microamperes, 100 nanoamperes. Currents are very small in subthreshold region because I have a very weak channel. I don't have enough electrons in the channel, and therefore the current is very small here. So that brings in an important difference between the two here. The BJT is exponential, but you can have very high currents. We've been seeing currents of 10 milliamperes, 100 milliamperes, that kind of a current you can have in a BJT. While in a MOS, the currents would be in microamperes, which, you know, will translate into the fact that if you have small current, if you go and look at GM, if you have small current, GM is directly proportional to current, right? So if it's proportional to current, then you have very small transconductance. And we all know that transconductance plays a very important role in the gain of the amplifier. Okay, so although the MOS is acting like a BJT, and in some respects is better than a BJT because it has no base current, and therefore it has infinite input impedance. But the drawback is that it has very low current, and therefore transconductance is low. But nevertheless, this is a very useful operation, and many low voltage or low power MOS circuits are built by, MOS amplifiers are built by operating the MOSFET in the subthreshold region, deliberately operating it in subthreshold region and making very, very low power amplifiers. So that's one area where MOS transistors are in subthreshold are useful. All right, as I said, our focus is not on subthreshold. Our focus is back again into this particular region here, saturation. So now what we have done is we have looked at MOS operating in all these regions here. We have looked at in saturation region, we have looked at in triode, and we have seen the subthreshold also. So what we are going to do next is go a little deeper in the saturation region here, and specifically we'll look at a small signal model, because eventually for analyzing amplifiers we need a small signal model here. So what we'll do is, you recall, I think I've shown a picture like this earlier also. It's not specific to a MOS model. Any device model, for example, I can break it into two parts, a large signal and a small signal. And a large signal, I can have a DC model, which is also a low frequency. Low frequency acts like DC. Or I can have a large signal dynamic model where signals are varying, with time, and the model is suitable for analyzing transistor in that domain here. The other one is small signal. Signals are small enough, and how small effectively, is determined by the fact that I want a linear model. Okay, so the reason why we go to small signals is that we can approximate the device operation as linear operation, and we'll see small signal models are also, it can be low frequency, where I don't have to bother about capacitances, or it could be high frequency small signal model where I have to include capacitances into my structure here. So these are the models here. So far what we have seen is a sort of DC or a low frequency model in saturation region, in linear region, and in subthreshold region here. Now what we'll do is we'll look at from here we'll derive a small signal model in the low frequency region here, and then what we'll do is we'll add capacitances and we'll get a high frequency model as well. Okay, so we'll have a DC model which we will use for calculating the bias point and DC analysis and all of that. So we'll have this model here, and today we'll derive the low frequency and the high frequency small signal model. So we'll have all the models for the MOSFET, and after that we are ready for amplifiers. We can begin analyzing and designing amplifiers here. Okay. All right, so note that the DC model that I just talked about, that you see here for a MOSFET, can be represented by a very simple circuit structure shown here. MOSFET, as we know, has 4 terminals: gate, drain, source, and body. Source and body, between source and body, note that there's a diode here. So we have explicitly shown a diode here. Between drain and body, there's also a diode here. So we've shown here. And normally, as I said, what we do is we keep both the junctions reverse biased. So the diodes are in cutoff state, reverse bias, and a very small leakage current is all that flows between these 2 points. Okay, so a very small leakage current flows here, a small leakage current will flow here, and usually we neglect those leakage currents here. Between gate and source, I don't have any current, so it's shown as open circuit, assuming it to be an ideal insulator. And between drain and source, obviously I have a current, IDS, and we have an expression for IDS in saturation region. Okay, so that's the description of how your MOSFET from a circuit point of view looks like. So it's a voltage dependent current source here. This IDS depends on gate to source voltage, it depends on drain to source voltage, and also depends on the body to source voltage here. The body, remember what it does is if you change the body to source voltage, it changes the threshold, and as the threshold changes, the current also changes. So this current that you see here, voltage dependent current source, depends on many voltages. It depends on gate to source, and depends on body to source, and also depends on drain to source. All right, and we have an expression for this current here. So that's the description of your MOSFET. And if, as I said, models you can make more and more accurate. For example, we know that the gate or the oxide, especially now, oxides are in few nanometers, and therefore, there's a lot of leakage current that flows through the oxide as well. So one may want to include something in between gate and source to model the leakage current. Now, associated with each one of those terminals, with the source and the drain, there is a resistance here. Note that somewhere here I'll make a contact, and from the contact, my carriers have to flow through N plus and then reach the channel. And so there is a small amount of source resistance also here. So if you want to make it more accurate, you should include a source resistance here. And similarly, include a drain resistance here and a body resistance and a gate resistance and all. Okay. And but usually they're relatively small compared to the important resistance, which is the channel here. Okay. So now we have to derive the small signal model here. And if you recall, we had in an earlier lecture right in the beginning, we had seen that any 3-terminal device that you have, and it's a unilateral device, meaning the output is affected by the input, but the output doesn't affect the input here. Okay, so unilateral device, 3-terminal is small signal model is nothing but from the input side you see a resistance here Ri, from the output side you see a voltage dependent current source, and you see an output resistance here. Any 3-terminal device which is unilateral, a small signal model will be given by these 3 elements here. And now what I want to generalize this to is as a 4-terminal device. Okay, so now I've added a 4th terminal. All right, so there's a 4th terminal here, and this one, and now and the 4th terminal also acts as an input. The output is between these two. So now what happens is the output current I naught depends not only on the input voltage here. We have 2 inputs now. Think about it. V1 is one set of input between these two pair of terminals, and V2 is another input between this 2 pair of terminals here. And this is the common. Let's say we take it as the common terminal. Okay, so we have 2 inputs. So I naught now is a function of V naught, obviously, and I naught is a function of V1, and I naught is a function of V2. Right? So it's a function of all 3 variables here. Now, what will a small signal model look like? Well, if you go and look at this particular case for a moment here, I naught depends on V1 and I naught depends on V naught. Is dependence of I naught on V naught, how does it show up in the small signal model? R0. Why? Because the I naught is along the same pair of terminals and V naught is also along the same pair of terminals, and therefore it comes around as a resistor here. Dependence of I naught on V1 shows up as a voltage dependent current source, because I cannot represent it by a resistance. It depends on some other voltage here. So it has to be a voltage dependent current source here. So now if you think about I naught here, depending on V1, depending on V2, and depending on V naught. So I naught's dependence on V naught will show up as a resistor. I naught's dependence on V1 will show up as a voltage dependent current source. And we will call it here as, let's say, GM1, V1, referring to V1 source. And I naught's dependence on V2 will show up as another dependent current source. We will call it GM2 multiplied by V2. And from this side, the dependence of I on V will show up as an input resistance. So we can easily generalize that for this 4-terminal device, it will look like this here. My small signal model will appear as shown here. Okay. This one is a current source, taking into account the input voltage V1. This one takes into account the input voltage V2. This one is an output resistance. So we have 3 elements here. This device, looking at it from the input, we have a resistance here. And from here, looking at the input, we have a resistance here. But I have shown here as an open circuit. So actually the resistance is going to be infinite. Because we are saying, when I show it as an, all right. So if some current flows here, then you will have some resistance here. Let's keep it general. So between here and here, as you change the voltage, some current may flow into this particular terminal, and that will show up as a resistance R2. So for a 4-terminal device, we can easily generalize it into this kind. Okay. All right. So let's come and look at then the MOSFET here. So in a MOSFET, can we guess how the small signal model of a MOSFET will look like? Note the drain current. So the diode is open circuit. Okay, it's reverse bias, it's open circuit, so we're going to leave it out. There's hardly any current flowing. Similarly, between source and body, it's also reverse bias. There's very little current flowing. So we'll ignore it. So what you have then is between gate and source, there's an open. Between source and body, also an open, because reverse bias diode is like an open circuit. And between drain and body is also an open. So all that you're left with is one current source, and it depends on gate to source voltage, drain to source, and all that. So can you see that if I do all my calculation, it will look like this small signal model. Just look at the figure for a moment. Between gate and source, I have nothing here. Between source and body, no current flows, nothing here. Where is this first term coming? GM-VGS, because my drain current depends on gate to source voltage. So I get GM-VGS. R0 comes about because my current depends on drain to source voltage. So that's R0. And what is this? GMB-VBS. Well, my current also depends on the voltage applied between body and source. So I have a current source here. Right? So what I have now is all these gate, drain, source, and body. We have open circuits everywhere except between drain and source, and we have these three elements. Okay, so that's what my model will look like based on the discussion that we had. The rest of it is actually deriving now what is the expression for GM, what is the expression for GMB, what is the expression for R0. So all those detailed derivation is for that. So let's quickly go over it and see how to do this here. Okay, so this is the model for my MOSFET in saturation region. So I'm building a small signal model in saturation, and that's why I'm starting off with the current equation which is in saturation region. Okay, so in saturation, my current goes beta n by 2 VGS minus VTHN square 1 plus lambda times VDS. And if you recall, the procedure for building small signal model is, well, we say my gate to source voltage has a bias component plus a small signal component. My drain to source voltage has a bias component and a small signal. Similarly, source to body has a bias point and a small signal. And in response to that, my current will have some bias value, DC value, plus a small signal component. Okay, I'm deliberately using the word bias because note, the small signal values VGS can also be DC. There's nothing in the derivation which says that VGS has to be AC or whatever is, all that it says is that I have a bias point, which is a DC, and the extra voltage that is there can be a DC, AC, or whatever it is. Okay, all that it says is I have a small voltage, incremental voltage, in addition to my bias point. Okay, so what you do is you take each one of these values here, substitute it here. You substitute in VGS this value here, and so you'll get a long expression. And in small signal model, what we are looking for is a relationship between the small quantities, small IDS, small VGS, small VDS, and small VSD. That's what we are looking for. And what kind of a relationship? A linear relationship. Okay, so that's what we'll do here. So what we do is we substitute all the values here. You can see there is one change that we have done. Note that the threshold voltage I have said is a function of source to body voltage here. And that's why, please don't take it, maybe the brackets have not been properly used. What it denotes is not a multiplication of threshold voltage with this, but it denotes that threshold voltage is a function of source to body voltage. Okay, it's a function of source to body voltage. That's what it denotes here. Okay, and so all the values have been put. All that we have done is substituted. And as I said, what we are looking for is the relationship between small values here. And what kind of a relationship? A linear relationship, right? So what we do is we take IDS here and we take IDSQ on the right hand side. And then there is a little bit of algebra here where we ignore all nonlinear terms. We ignore all nonlinear terms. You can see here we have square and all of that. So we ignore all nonlinear terms. I'm not going to bother with the algebra right now. And so we end up with this term. Okay, after doing all that. Some of you can try and see that the relations are correct here. Okay. Now, when I go from here to here and I'm ignoring higher order terms, I'm making approximation. I'm making approximation, and that's where my model becomes approximate. And this is where I can, I can derive that under what conditions will my model be accurate. Okay. And so note that it will always be inaccurate, first of all, because you've ignored terms. And depending on how small you keep these voltages, the accuracy of the model would increase. Okay, so I'll show you some later on here. So this is what we get here. After from here to here, we get this here. So note that there are three terms into it. IDS depends on VDS, IDS depends on VGS, and IDS depends on VBS. All of these are small signal quantities. Drain to source voltage, gate to source voltage, body to source voltage. Okay, and this is what we represent it as. The one which depends only on VDS, we write it as VDS by R0. The one that depends on VGS, we write it as transconductance, GM. And the one that depends on body is also a transconductance. And to distinguish it from the normal transconductance, we add a term body, referring to that this transconductance is with respect to body terminal here. So we get IDS is VDS by R0, GM VGS, and GMB VDS here. And as I said, one can look at it here, these expressions, and one can have now terms R0 depends on 1 over lambda IDSQ. So it tells you that the value of R0 depends on the bias point. We know that all small signal parameters depend on how you bias the MOSFET. So it depends on the bias point here. Similarly, GM, we have two expressions. GM is 2 IDSQ VGSQ minus VTHN. Another way of writing it is same as square root 2 IDSQ times beta here. So both are same. Sometimes this is convenient, sometimes this one here. GMB is GM times a factor here, eta is given here as gamma, is related to body parameter here, and all of that. Okay, so we have expressions for R0, we have expressions for GM, and we have expressions for GMB. All of these come from here, basically from here. Okay, so this is the model that we have. This is the most important slide for our course here, because all the time we'll be using the small signal model. And you have to know what the small signal model is. Very simple, 3 terms, and you have to know how to calculate each one of these values here. Once you bias the MOSFET, you know the drain to source current, you know the gate to source voltage here, so you can calculate GM and you can calculate R0, GMB, and so everything else is known. As I said, 2 phi f and gamma and all of that are all given to you, and all you have to know is your bias point. Once you know the bias point, you have all these parameters here. Okay. Now, this model is accurate under certain conditions here. One of the most important assumptions that we make in derivation of this particular model is here. If you note here that what we have done is this dependence of drain to source current on VGS, if you look at it, there's a square. And there will be a linear term also, but you can see here that if I take this term in the bracket and expand it, ignore this one for a moment. If I take VGSQ plus VGS square, and if I expand it, I will get a linear term depending on VGS, and I will get a square term. And what I'm doing is, I'm ignoring the square term. This is one of the most important assumption that I'm making when I go from here to here. And this is the most important contributor to errors that happen. Okay, and so what happens is, this is the approximation that we are making. We are ignoring the VGS square term, and it is showing you that under what condition can you ignore the quadratic term where VGS square term is there. If you satisfy this condition, VGS is much smaller than twice VGS minus the threshold voltage. Because you can go back and what you do is you expand it and then you compare the linear term versus the square term, and this is what you end up with. That under this condition you can ignore the square term, the quadratic term. Okay, and here I'm showing you the kind of errors that you get here. So effectively, if you want to know how accurate is your small signal MOS model, what you should look for is the ratio of small signal voltage, gate to source voltage, divided by this VGS minus VTH. Okay, so look at this ratio here, and I've shown here that if this ratio is 0.1, then the error is minus 4.7%. If the ratio is minus 0.1, the error is 5.26, and you can see how the error increases. Okay, so if you have to know how small should my incremental gate to source voltage, how small should it be? Well, it depends on how much error are you willing to tolerate. And if you're willing to tolerate up to, let's say, 10 to 11% error, what it says is VGS by VGS should be about 1/5 of the excess gate to source voltage. You can call it the, VGS minus VTHN, people call it overdrive. VTHN is the place where you start creating a channel, strong channel, and any voltage above VT is like an excess voltage or an overdrive voltage here. Okay, so gate overdrive voltage here. So it depends on what is your small signal voltage compared to VGS minus VTH. That's what defines the error. Okay, that's the most, as I said, determines the validity of your model here. And you can see, as I said, now note if you recall that in a bipolar transistor, your small signal model was valid when your base emitter voltage was much smaller than What was the relationship? Small signal base emitter voltage VBE was much, much less than VT, the thermal voltage. So on the right hand side, we had KT by Q, which was 26 millivolts, right? And therefore, in a bipolar, my model was accurate if I could take the small signal base emitter voltage as maybe 5 millivolts, 2 millivolts, something of that kind. Because on this side, I had KT by Q, which was 26 millivolts. Now, if you look at here, if I'm looking at 10% or 20% error, then 10% error. So I'm looking at VGS by VGS minus VTHN, which is 0.2. Now imagine that threshold voltage is 1 volt and you bias your transistor at 2 volt. Gate to source voltage is 2 volt. So VGS minus VTHN is 1 volt here. VGS minus VTHN is 1 volt. And which means that the small signal gate to source voltage can be as large as 0.2 volt under roughly 10% error. Can be as large as 0.2, which means 200 millivolts. So note the differences. In a bipolar transistor, you can apply base emitter voltage, which is of the order of few millivolts, 5 or 6 or something. That's all. If you go beyond that, the model becomes highly inaccurate. While in a MOS, you can apply up to 200 millivolts, 100 millivolts, 150 millivolts, and the model is reasonably accurate. Why the difference? Why this difference between MOS and bipolar? Why is there a difference? Why is it that I can apply a much larger small signal voltage in MOS as compared to bipolar? Exactly. So bipolar was highly nonlinear. Bipolar was, remember the relationship between the collector current and base emitter voltage was exponential. And therefore you have to keep your base emitter voltage really small in order to use a linear approximation. While here, the relationship between drain current and gate to source voltage is square, quadratic. And therefore, I can apply a much larger voltage and still my model is reasonably linear. Okay, so the non-linearity is much smaller here. And therefore, my model is, I can apply much higher gate to source voltage. Okay, so that's the difference between the MOS and bipolar here. All right, so that's, so we know now, we have a model for MOS in saturation region, small signal model. The only problem is that this model can be used only under low frequency condition, because I used a DC equation to derive this particular model here. We don't have any capacitances. If I add capacitances here, then this will become a high frequency small signal model. Okay. So before I do that, very quickly, whatever we have derived for NMOS, whatever we have said for NMOS is also valid for a PMOS, but with some very crucial changes that you have to keep in mind. Note the differences here. I'm showing you a PMOS, and PMOS, of course, is made in a, as I said, in a N region, N well here, and the source and the drain are P plus, and the gate is over here. Now note that I have to create a channel, and the channel has to be of holes, so I have to create positive charge here, so I apply negative voltage here. So note the first difference, that I have to apply negative gate voltage. I have to apply a negative gate voltage to create a channel. In an NMOS, I have to apply a positive gate voltage to create a channel. Okay, so that's the first difference that you see here. And therefore, VGS has to be negative, and threshold voltage is also negative. I have to apply a certain negative gate voltage before I start getting a strong enough channel in my device here. And so threshold voltage is also negative. And the typical value that we'll take for this particular course is -1 volt. So if I apply -1 volt or larger, I get a strong channel. If I'm below -1 volt, below in the sense of magnitude. So if I'm -0.5 or -0.4, I don't have a strong channel. I'm in subthreshold. Okay. So the other thing is, so gate voltage is negative, and we apply drain to source voltage also negative. So my source is, let's say, ground, and I apply a negative voltage to the drain, which pulls in holes from here, from the source. Holes are pulled in, and they flow through the channel, and they reach the drain. So my normal operation is drain to source voltage is also negative, and drain to source current is also negative. Now, typically what happens is, in these devices, if a current is going into a terminal, is taken as positive direction. Okay? So in a MOSFET, if you recall, we had a source and we had a drain, and electrons were flowing from source to drain. And the current was actually flowing from drain to source. And so the current was flowing into the drain. and therefore the current was positive. In this case, the holes are flowing from source to drain here, the holes are flowing out, and so the current is flowing out of the drain terminal, and we take that direction as negative. So note the following here. VGS is negative, threshold voltage is negative, drain to source voltage is negative, IDS is also negative. Okay. So now all the model that we have developed for N-type is also valid for a P-type, except for these changes here. And I'm sure you can see that what is the counterpart of VGS in NMOS? Remember, VGS was positive in NMOS. What is positive here? What is the counterpart of VGS here? So if I take my equation of NMOS, can I just substitute VGS for a PMOS also? See, the counterpart is VGS is negative in a PMOS, but VSG is positive, right? So if you just flip it, VGS is negative, but VSG is positive. And in VTP, if I take an absolute value, and instead of VDS, if I take VSD is positive, and instead of IDS, I say ISD is positive, right? So if I make those changes, all the equations that you see for NMOS are valid with those changes here, okay? So the point that I'm trying to make is the following. This is NMOS. Drain to source, you can see here, gate to source is positive, drain to source is positive, current is flowing here. This is PMOS, current is flowing from source to drain. The voltage gate to source is negative, source to drain is negative. But if you make the following change here, instead of saying gate to source is negative, you can say source to gate is positive, source to drain is positive, and the current is flowing from source to drain. And now you can see the two are exactly the same. And all that I need to do is, wherever you find VGS in an N-channel MOSFET model here, VGSN, you just substitute it by VSGP. Wherever you see IDSN, N referring to N-type, you make it ISDP. Wherever you see VDSN, you just substitute VSDP. And all the models, all the equations that we derive, they are valid for PMOS also. Okay, so keep that in mind. In a PMOS, current is flowing from source to drain. Source to gate voltage is positive, and source to drain voltage is positive. So these are important distinctions. And the reason why I'm saying is that most of the time what happens is, just as we concentrated a lot on NPN bipolar transistor, we'll concentrate a lot on N-channel MOSFET here, N-channel MOSFET based transistors and amplifiers. And as a result, what happens is we become very proficient in handling N-type transistors. And when we are given P-type, we fumble. Often mistakes are made because we don't emphasize it that much. Okay. So note that this was the equation that I had for NMOS. Just substitute. Instead of drain to source ISD, beta N remains beta P. VGS becomes VSG. Instead of minus VTHN, you put plus VTHP. And VDS becomes VSD. And you have a model which is valid. Okay. Now, if you take this particular model, and build a small signal model from here, what you will get is small signal model will become, from ISD you will get a small signal ISD here, and you will get GM. Instead of VGS, you will get VSG, and you will get GMB. Instead of VBS, you get VSB, and you get, instead of VDS, you get VSD by R1. So if you take this equation and derive a small signal model, you'll get this term here. Okay? Because we have reversed everything. From drain to source, we have made source to drain. From gate to source, we have made source to gate. And we've reversed all the terminals here. Okay? So you'll get this small signal model. Now you can see here, I can reverse it once more. Right? I can reverse it once more, and this becomes the same. Right? It becomes the same here. Which means what? The small signal model of an NMOS and the small signal model of a PMOS are exactly the same. They're exactly the same. Same model that you use for NMOS and same model you use for PMOS. The directions and everything else is the same. GM-VG is here, GM-BVB is here, R0 here. Except that the GM, when you calculate GM, you have two ISDQ, VSGQ plus VTHP, and similarly R0 you will use obviously the drain current corresponding to a PMOS. So same P-type, same PMOS model, and the equations are over here. Okay. All right, I don't think we have enough time, but let me introduce to you the capacitances that are there in your MOSFET here. Look at this picture. This is my N-channel MOSFET. Can we do these capacitors make sense? You can see 4 capacitances. Okay, so some of the easiest ones to understand are here. Do we know where this is coming from? What do we have between N plus and body? No. What is there? We know where there's a. What is there between? You have an N and you have a P. So what do you have? A diode which is reverse biased, and a reverse biased diode. There's a capacitance. We've already seen depletion capacitance. So that's the origin of this one. Similarly, between here and here, you have a reverse bias diode, and so that's the reverse bias diode capacitance here, depletion capacitance here. So these are the 2 ones here. Where are these coming from? Between gate and source, I'm showing a CGS, and between gate and drain, I'm showing a capacitance called CGD. Where are these coming from? Now, just keep in mind that a capacitance is what? Change in charge with voltage. Now, if I change my gate voltage, what happens? Are you seeing that charge in the channel changes? Where does it come? You know, if you increase the gate voltage, let's say, if you increase the gate voltage, you will require more channel charge. Where will it come from? Where will the excess channel charge come from? I have 1 volt at the gate and I increase my voltage to 2 volts. I require now a lot of electrons in my channel. Where will they come from? Where will these electrons come from? They have to come from some terminal. How many terminals do we have? Source, drain, and body. Where will they come from? Body? Does body have electrons? Body is p-type. Which is the source of electrons here? The source. The source is the source of electrons. Right? So what happens is, when you apply positive voltage and you require electrons, the electrons come from the source here. And they can come from the drain also. They come from the source and they come from the drain. From both sides here. Okay? That's the source of electrons. My channel, note, my channel here is connected to source and drain. I have a channel here. So you apply more gate voltage or less gate voltage. If you apply a lesser gate voltage, the electrons that were there in the channel earlier, they go out from this source and they go out from this drain. So what is happening is, you are seeing, yes, the channel is over here. And so it doesn't go like this here. It goes actually to the left or to the right. So the channel communicates with the gate through the source and the drain terminals here. So now imagine that I change my gate voltage to a larger value, and therefore I need more charge in the channel. The charge will come partly from the source, partly from the drain, and therefore I have 2 capacitances. The charge which came from the source side will appear as a capacitance between gate and source. And the charge which comes from the drain side, it will appear as a capacitance between gate and drain. Okay? So the source of capacitance is the channel here. Is this channel here. The channel charge enters the channel or exits the channel through these 2 terminals. Okay? And that's why I have a capacitance here and I have a capacitance here. 2 capacitances. Now there's one more point here. This gate that you see here, there's an overlap between the gate and the N plus region that you see here. There's an overlap here. And similarly, there's an overlap here. An overlap means I have a metal, I have an insulator, and I have an N plus. And this overlap also contributes to the capacitance here. And the overlap here also contributes to capacitance. So the source of the gate to source and gate to drain capacitances are then the channel and the overlap regions here in the overlap region. These are the sources of CGS and CGD. Now you can think of the following. As I've said, that if you apply a gate voltage, charge enters from the source side and from the drain side both, right? Now, if you go into the saturation region, if you go in the saturation region, What is the characteristics of saturation region? The current is no longer changing with the drain voltage, right? We said that the current doesn't change with the drain voltage. Why it doesn't change with the drain voltage? Well, if I change my drain voltage here, obviously it doesn't affect my channel charge. If it affects my channel charge, then obviously the current will change. So the first order approximation, as I change my drain voltage, my channel charge is not affected. And therefore, you can see that in saturation region, the capacitance between gate and drain will be small. Why? Because anytime I change, my drain voltage here, my channel charge doesn't change. So this capacitance is small, while this capacitance is large. So when I go into saturation region, what I will find is this capacitance is a large capacitance CGS. This capacitance is a small capacitance CGD. And of course, I have source to body and a drain to body capacitances which are there in my system. Okay. So again, we can't go into the derivation of each one of these. So there are two contributions to gate to source capacitance here. The first one that you see here comes from the channel, part here. And the second one comes from, there's an overlap region. There's an overlap between the gate and the N plus source region. That's the overlap here. Now note the following. C oxide is a value which will be given to you. So it's capacitance per unit area. And we have multiplied it by W and L. L is the length of the MOSFET and W is the width of the MOSFET. And there's a pre-factor term which comes in here, which comes from the details of the derivation. Okay, so we'll not bother about this 2/3 here, but this is the capacitance that comes in. It depends on the area of the channel here, W into L. The second one, note that there's no L. The second one is the overlap capacitance here. It only depends on the W. Okay, remember W is perpendicular to the plane of the slides here, perpendicular to the plane of the figure here. And so this capacitance is capacitance per unit length. Capacitance per unit length, and you multiply it by W to get this part here. This is a capacitance which is per unit area. And you multiply it by the area here and you get that. Okay, and that's how you get your gate to source capacitance here. Gate to drain is simply this one. As I said, gate to drain is an overlap capacitance. CGD is CGD0 times W here. All right. So this is the picture that we have for a MOSFET. Top view of a MOSFET.